I gotta be careful what I say here from now on. Apparently. Okay. I guess I have to click that I got it. Okay. Well, good morning to everyone. I think I'll start off by thanking Odina and Yersha for putting this meeting together. You know, it started years ago, it seems like, and COVID was not kind to them. Even through today, there's last minute changes, as you just heard. So I really appreciate your strength and determination in making this meeting happen. Thank you. So I'm going to start off sort of as a warm-up talk for my colleague Doug Harden. Let's see, there's something.
I just make it.
Okay. Sort of a warm-up talk for my colleague and give some of the basic kind of definitions and background. I should say that my talk reflects my own background. So I came through complex analysis. That's sort of my first love. And then on to potential theory, some numerical analysis, and more recent past, sort of particle interactions, point configurations, and the sort of thing that we'll be focusing on at this meeting. So I want to talk mainly about potential theory. So sort of an introduction to potential theory, if you wish. And there are several books that I'll recommend. This is not self-promotional, purely self-promotional, because we're giving you access to this book. Do you all have access? Did you all get the link? And I hope that works for you.
We spread it on the web.
Oh, okay. Okay, don't tell my publisher, please, about this, because okay, I don't want to get in trouble. But so a lot of what I have to say here is in this book, and includes a lot of our research over the past 10 years. Other of my favorite resources, my secret resources, are Landkoff's book on Foundations of Modern Potential Theory. This is an excellent source, particularly for Reese potentials. Mattila's book, where he deals with geometric measure theory, some aspects of geometric measure theory, which are quite useful in what we do. I have an older text that focuses on logarithmic potentials with external fields. This is strictly in the complex plane setting. There is a secret source, which is this work of Otsuka. Otsuka published in the Journal of Science of Hiroshima way back when. And as you can see from the number of pages there, it is in some sense a book published within a journal. So it's a great source of information about potentials in locally compact spaces. Okay, so why did I get into this business in the first place? And I had several motivations, and one of them was for energy minimization, that is, generating good nodes for sampling a surface. So we've got some surface, let's say a free space, it could be the surface of a sphere, and we want to choose a large number of points on that surface that are either uniformly distributed in some sense or distributed according to some prescribed density. So that's one problem, sampling, where to sample. Another is problems from physics where we have interacting particle systems, particularly say pair interactions, and you have knowledge about that pair interaction, and you put 1 million of these particles together, you know how they act pairwise, and you restrict them, say, to some set. Eventually, you want to know what happens to these points. What becomes of them? So what kind of um, order arises from these pairwise interactions? So that's a motivating question. And the third one listed here has to do with error correcting codes, the practical aspect of, well, let's say we want to communicate, we want to send words to each other. We don't want them to clash with one another. We want them to be separated and sufficiently so that there's no ambiguity when we send a message. So this is a problem that can be viewed as a fast packing problem. We want to maximize the separation among points. Okay, so let's start off in terms of energy. We will start off in a general setting where you have A is a compact set. There's a metric space with a metric M here. And I want to talk about particles pairwise interacting. And so I'll be discussing a pair potential. So throughout, K of X and Y is our pair potential. It's simply a mapping of A cross A to the extended reals. And I'll always assume that it's symmetric and lower semi-continuous. And the most popular potentials that you will likely encounter are either inverse distance potentials, which we'll be talking a lot about. So will Doug be talking about inverse pair potentials, which are simply 1 over this metric distance to some power S. S is sometimes referred to as the strength of the interaction. So that's a Riesz potential of a Riesz kernel with parameter S. And of course, Gaussian kernels that arise in probability theory so often, which are described here. And can you see this pointer? Yeah, can you see that? Okay, okay, great. So these are not independent guys because you can express the inverse distance potentials in terms of the Gaussians. So that the good news about that is if you prove something about general Gaussians, general in the sense that it holds for all alpha, then you can say something about these Riesz guys, about the Riesz potentials and kernels. Okay. So now we'll start off talking about discrete energy. And by the way, I'm going to be going probably pretty slowly, maybe too slowly, but don't hesitate to ask questions, interrupt me. That would be great. We have a lot of time, but we're not pressed for time here, as I understand it. So please don't be shy and ask questions. Okay, so we'll start off with a discrete energy. What do I mean by discrete energy? So we're given a endpoints, let's say. Here it's denoted by omega sub n. That will be my standard notation. Omega sub n as a set of endpoints. More generally, when we have continuous kernels, we can allow some of these xi's to be repeated. So that is, this to be viewed as a list rather than a distinct point set, okay? Even though it's written that way. So what do I mean by the K energy of this set of points or configuration? I'll call it an endpoint configuration. What is the K energy of this endpoint configuration? Well, we just take all the K interactions between the points of the set, with the exception that we don't allow the same point. Okay, so we take I, not J. We sum up all these pairwise interactions, and that's what I call the K energy of this finite point set omega n. And what we're interested in are things you might refer to as what happens at absolute zero temperature. Okay, we're interested in minimizers. Okay, is that good?
That's right. That's
For people. Okay, absolute zero. So we want to look at all these endpoint subsets of the set A and find point sets whose energy is minimum among all endpoint subsets of A. And that I'll denote by this calligraphy E sub K. So here we have italic E, which is just the energy itself. But once we go to this calligraphy E sub K, that we're talking about minimizers there. And if there will be, thanks to our assumption about lower semi-continuity, there will be an endpoint configuration that attains this minimum. And I'll use a star, asterisk, or whatever, to denote such a set of endpoints, referred to as an endpoint equilibrium configuration. And it's easy to see that these optimal points, these elite equilibrium configurations, are not in general unique. So if we want to be thinking about particles interacting, we can think of the electrons that are confined to, say, the surface of a sphere. They're interacting via, say, repulsion, Coulomb potential, or something like that. And we're concerned about, well, what happens? When do they come to rest? What do they look like? Okay, so I just put this slide up so there's a comparison. So if you were watching me playing darts last night, so we had a wonderful meeting at the flight park, and we had a dart competition, dart throwing competition. So so mine was a sort of random like, and I'm not very good. My dart throwing. So imagine we're throwing darts at the surface of the sphere. This is a unit sphere, say S2, embedded in R3. But we'll throw them at least randomly according to surface area. Okay, so and I do it 3,000 times, and here's the points that I get. So this is just IID random points on the sphere, 3,000 of them. And here we have minimum energy points displayed on that very same sphere. These are, in fact, minimum Reese energy points where that Reese parameter S guy is equal to 2. And so you can see the contrast is quite dramatic. If you look here, we see points that are really close together. Okay, some points that are very close together. That's not always desirable. And also we find regions where there are no points at all here, as compared with what looks rather uniform over here. Okay, so energy minimization can give us good point configurations, and we're interested in, well, how do these point configurations behave? How do they behave in a macro sense? That is to say, the number of points increases. What do they look like locally? Do they have good separation? Do they have good covering properties? And for that purpose, it's often more convenient to deal with a measure than a set of points, to think of it as a omega n really as an empirical measure. And by that, I mean the following. If here's our set omega n, our configuration, what we do is we put a mass of amount 1 over n at each one of these points. And what we get here is denoted by nu of n. It's simply the normalized counting measure in the points of omega n. And this is called also the empirical measure, as I mentioned. And so what our concern is with, if we want to understand what point sequences look like, we might want to study these measures. How do these measures behave? Do they converge in some sense? So, okay. So what about convergence? And sort of the weakest type of convergence is weak star convergence of measures. What do I mean by weak star convergence? I mean that if you have a sequence of measures, here denoted by v sub n, and they're all supported on our compact set A, then they're said to converge in the weak star sense to a measure mu, provided the integral of a continuous function on A against mu n in the limit is the integral of that function against mu. Okay? That should be true for every continuous function on our set A. If that's the case, then that is called weak star convergence. And it's a simple exercise for you to do when you first learn about weak star convergence, that if you are integrating a lower semi-continuous function and you have a sequence of measures mu n that converges to mu weak star, then the integral of f against that limit measure is less than or equal to the lim f of the integrals of f against the d mu n. Why is that? Well, remember, a lower semi-continuous function, what is that? It's just the limit, the pointwise limit of an increasing sequence of continuous functions, right? So I know I would have equality if we had continuity. I don't have, but I do know we don't have continuity, but I do know that continuous functions approach from below. So therefore, I get this inequality here. So this is a very simple but quite useful type of inequality. And now, we get to our first exercise. So we'll try to throw out some questions. Some might be very easy, like this one is fairly easy. Others might be quite difficult. But from time to time, I want to put in some questions and hope to challenge you to work on them on your own or discuss them with us later or with Alex Vlasiak, who is serving, so to speak, as a tutor for this mini course. So what is the exercise? The exercise is this. If we're looking at the unit circle, say the unit circle in R2, and we take equally space points and we look at the normalized counting measures in those equally spaced points and look at the limit as the number of those points gets larger and larger, I think you'll all agree that that limit is simply the uniform measure on the circle, right? Just the vague measure, what we would call d theta over 2 pi. Well, it's a classic example of Weil that if you take, instead of equally spaced points, if you take points on the unit circle given here via an irrational multiple of I k pi, so I is the square root of -1, k is running from 1 through n. If you look at these points, then they will sit on the circle. They won't repeat, okay, as you go on. This is actually a sequence, a infinite sequence, right? We truncate at each end. And so the fun problem is to prove that these normalized counting measures in these points are also uniformly distributed on the circle. So as a first challenge for convergence in weak star measure of convergence, then this is a great way to get into the subject. Okay, so that was a discrete problem. There was a fixed number of points that we were interested in. We wanted to minimize the energy. There's also a continuous problem. And the continuous problem is essentially where we replace discrete points by measures. So let's talk about this so-called continuous problem. And here we need some notation. We'll use this calligraphy M with A to denote the collection of all probability measures supported on the set A. Okay. And again, our kernel K is symmetric and lower semi-continuous, and just for simplicity, I'll assume it's non-negative. Lower bounded is sufficient. Then we're going to define a continuous energy of a measure. What is that? It's the double integral of on A cross A of mu, the kernel, integrated with respect to mu cross mu. So that's our continuous energy. And we're interested in minimizing that energy, where we want to minimize among all possible probability measures supported on the set A. We minimize this double integral, and that minimum is referred to as the Wiener constant. And in complex variables, it's often referred to as the Robin constant. So that is an important quantity that you'll see mentioned several times in the next hour or two. And an equilibrium measure, what do we mean by that? We mean a probability measure supported on A, whose energy attains the value of the Wiener constant. There is stuff written in red here at the bottom of the screen. And it's actually important. It's really important for what is going to go, you'll hear later, especially from Doug. And that it's possible that you're in a situation where this Wiener constant is infinite. In other words, no matter what probability measure you plug in here against this kernel, you get infinity. Okay. In which case, well, you have the unusual situation that every measure is an equilibrium measure. Okay, so there are authors who prefer to say, oh, no equilibrium measure exists. I prefer to say every measure is an equilibrium measure, and you'll see why in the next theorem that we talk about. But this is a particularly interesting case because it's sort of in potential theory, we talk about sets with the Wiener constant being infinite as sets having capacity zero. Capacity zero means, hey, you're so small, you can't hold a charge. Okay, you try to put down a charge on that set, it jumps off. Okay, so that's what we mean by the Wiener constant being infinite. It has capacity zero. Here, capacity is simply defined as 1 over the Wiener constant. Okay, so but so these sets have been ignored in the literature. They just say, oh well, we'll prove a result and everything is fine except for a set of capacity zero, and you know the theorem works and all of these sorts of things. But actually, these sets arise in many important occasions, and particularly if you take a set, say, of dimension 2, and it's embedded in a space of dimension 4 or something like that. Well, that's great, but what if your kernel has a Riesz parameter which is very large, in which case that set will have capacity zero. Okay. So there are situations that we'll be talking about where we're dealing with sets, indeed sets of capacity zero, and we want to say something about point configurations on it. Okay. All right. So this is what's known as what's beyond potential theory that we'll get to at the end of my talk and the beginning of Doug's talk. So we mentioned an equilibrium measure, but how do you know it exists, and what do you need? What tools do you need to show that they exist? And it's fairly straightforward. By the way, by the K potential of a measure, we simply mean the integral of the kernel K against the measure mu. And that's denoted here by the symbol U, subscript K for the kernel and mu for the measure. And so this is the K potential. And what is the energy? The energy, which was that double integral, can be simply written as the integral of your potential against the measure for that potential. Okay. And the way we prove the existence of an equilibrium measure is just to look at the inf, right? Look at the inf of the energies and pick out a sequence of measures that for which that are converging to that infimum, and want to say something about a limit measure. And for that purpose, we use what's called the principle of descent. So this is in potential theory. This is a very useful result and not difficult to prove. What does it say specifically? It says that if you are given our nice kernel K, if we have a sequence of measures mu n that converges weak star to a measure mu, then the potential of that limit measure is less than or equal to the lim inf of the potentials of the mu n's. And also the energy, the K energy of the limit measure is less than or equal to the lim inf of the energies of the mu n. So another way to say this is that, hey, your potential, if we think of the potential as a function on this collection of measures, okay, the potential is a lower semi-continuous with respect to the collection of measures mu. Okay, that's what this is saying. Value is less than or equal to the lim inf. The same thing with the energy. The energy is lower semi-continuous with respect to this collection of measures, probability measures. So that's how you summarize the principle of descent. Okay, so now we get to one of my favorite theorems. I really like this theorem because I like its proof, and I'm going to drag you through the proof. let's talk about the statement of it. First of all, it's this kind of compilation of a lot of important mathematics that was done by people like Otto Frostman, Choquet, Fekete, Sega. These are all names from classical analysis, and they've contributed in some sense to this result. It's a very simple one to state, and the methods of proof are interesting, they're fascinating. So we're going to go through it. What does it say? Well, first of all, it connects the discrete problem to the continuous problem. Okay, there's not surprising that there's a connection, because if you discretize that double integral, somehow you're going to get, an energy sum. But we have to worry about that diagonal business. Remember, right? You can't have I equal to J. So when we deal with energy for discrete sums, we want to take I, not J. Whereas in the integral case, we don't separate out the diagonal in any way. Okay. So there's work to be done, so to speak. All right. So okay. So what does the statement say? It says this. Look at your minimum K energy for endpoints on your compact set A. Divide it by n squared, and then take the limit as n goes to infinity. And it says that this limit exists, it's going to exist, and be equal to the Wiener constant. Remember, the Wiener constant was just the minimum continuous energy, double integral, minimum continuous energy. Okay. So, okay. So in particular, if this guy is finite, then this is telling us that the energy, the K energy of endpoints on the set A will grow like n squared, like the square of the number of points. Okay. And moreover, it tells us about the behavior of your discrete minimum energy points. Remember those omega n stars? Those were the minimizers, the discrete minimizers of your energy. And it says, hey, if you look at the normalized counting measures in these points, in these minimum energy points, every limit measure of this sequence, limit in the sense of a weak star limit, every limit measure of these empirical measures is going to be an equilibrium measure for the continuous problem on the set A. So that kind of gives us a sense of where points will go. What will they look like on a macro scale if we let the number of points increase? What will they look like? Well, they will be converging in this weak star sense to an equilibrium measure for the continuous problem. So if we knew that equilibrium measure, then we'll sort of know how those points are behaving in a limit. So that's useful in that sense as well. Okay, so
Sorry, so
yeah,
K as above just means K lower than continuous.
yeah, you need it lower. Okay, so lower semi-continuous on A cross A, so it's going to be lower bounded. So it's lower bounded, and it's kind of amazing that it's so weak. The conditions are so weak. Always, so assuming it's symmetric, you can get rid of that as well. But lower semi-continuous, that's the essential feature.
Okay, but so it can be unbounded or
Yeah. So we're going to be doing a lot. Think about those Reese guys that I mentioned earlier, right? 1 over distance, right? They blow up. So it's going to blow up when x equals y. So
and if the
It could be.
constant is infinite, this also works.
Yeah. It doesn't tell us anything, but it works. It's sort of vacuously true, right? Because suppose this is a good point. Suppose this guy is infinite, right? Okay. Well, take any sequence of minimizing points. Look at any limit measure. Every measure is an equilibrium measure. So this statement here is vacuously true, right? That weak star limit measure is going to be an equilibrium measure for the continuous problem. Okay. Thanks for that question. Yeah.
The theorem you're presenting here is 4 points that are constrained to the rate of the so this theorem is floating around with K only those continuous. I also prove not constrained to be on a set, but let's say
Yeah, yeah, so, okay, so this is a, a nice area to go off and talk about. And that's where we have an external field present, okay? And often that's a constraining, we have a constraint on our problem. So we might work in all of RD. Let's say we work all in R, points can be anywhere in RD, but, and they're interacting among themselves, but there could be some external influence, okay? And so this can be viewed just as a more general kernel. So this is a very general kernel that can include the external field. So we take, say, a Coulomb interaction locally, and we have some other something that repels from infinity or something like that. It will be a constraining type of external field. So, and this works, yeah. So it's very general indeed, and it's for general metric spaces. I mean, so it's not restricted to Euclidean or anything like that. Okay, so so I need so I need your willingness to go through the proof. Okay, are y'all going to help me do this? Okay, thank you. I mean, I really appreciate that because I don't want to just be listening to myself talk here all morning. But all right, so I just broke it down to, I think, 3 steps. And the first step is, and I put here as an exercise. And so for you all to prove on your own, and it's something it's rediscovered every once in a while. Oh, I made this great discovery. Look, if I take the minimum energy here, I divide it by n times n minus 1, I get an increasing sequence. Okay, but that was known, 50 years more ago. So that's no great shakes. But so it's a fun exercise to do on your own. You just look at n plus n points, and there it's minimum energy, and you sort of pull out a point, look at how that affects things, and you get a lower bound, and you'll be able to prove that this is an increasing sequence. And so since it's an increasing sequence, it will have a limit, and we'll denote this limit by tau sub k of a. So the limit of this ratio here is what is called the k transfinite diameter of a, and it's often associated with the name of theta. Okay, so okay, so here already we have that the minimum k energy divided by n squared has a limit. Okay, I'm just writing the n squared as n times n minus 1. Okay, so the next step is to show that this transfinite diameter is less than or equal to the Wiener constant. Remember, if we go back, what we want to show here is we want to show that this limit is the Wiener constant, right? So we want to show that that's part of it. Oh, okay. Hi, man. So my student from Vanderbilt. So we want to show that this transfinite diameter is less than or equal to the Wiener constant. And for that purpose, we're going to use a simple fact, which is that the minimum K energy is not greater than any average energy. Okay, the minimum energy is not greater than an average. Okay, so that's quite trivial. All right, let's see how we're going to use that. So let's go ahead and select points, endpoints, IID, so randomly distributed on our set A according to the equilibrium measure. So this is the equilibrium measure. U sub A is the equilibrium measure, the continuous equilibrium measure for our problem. And we'll choose endpoints that are IID randomly distributed according to that. Here's our energy. So our energy is right here. Okay. And so if I want to compute the average of that energy, I need to integrate this sum with respect to each one of these variables. Okay, x1 through xn. So you get an n-fold integral here, which looks a little scary at first, right? Looks a little ominous, but if you just focus on it, you see it collapses because look, essentially you're only integrating a function of 2 variables, right? It's just these two xi and xj. All the other guys integrate out to 1 because they're probability measures. So in fact, you only have essentially one term, right? And that one term is this, okay? But it's repeated n times n minus 1 times. Right, easy. Okay, so the minimum energy, which is indicated here, is less than or equal to n times n minus 1 times this integral. But that's, of course, the double integral of an equilibrium measure. And that is, by definition, whatever what we call a Wiener constant, or just here, the energy, the IK energy of mu sub A. So what we get from this is that the minimum discrete energy divided by n times n minus 1 is less than or equal to this I sub k of mu A, which is the same as the Wiener constant. In other words, if we let n go to infinity here in this inequality, we get that the Fekete constant, transfinite diameter, is less than or equal to the Wiener constant. Okay, everybody good with that? We survived step 2. All right, step 3. Step 3 might be more fun to write on the board, but okay. So here we'll have to go a little slower. So what we want to do is establish the inequality the other way around, right? We want to show that the Wiener constant is less than or equal to the transfinite diameter. So we can always select a subsequence of the probability measures being the measures that normalized counting measures in the discrete minimum energy points. So this guy right here, the xi stars, these are the minimum discrete energy points. And we form the normalized counting measures in these guys. And we pick out a weak star limit. So why do I know it has a weak star limit? Something called Helly's lemma, but what is it really saying? So, okay, so let's talk fancy talk. We talk about sign measures, or right, the dual of continuous functions on the set. And what we know is that if you have a compact subset, it's sort of sequentially compact. If it's a bounded subset of the dual space, it's sequentially compact. Okay, so I can always select some sequence of measures that converges to some limit measure in the weak star sense, which I denote here by mu. All right, so let's see what we could say about that. So here's our limit measure mu. I take its energy. That's what's just expressed here, now I can use the monotone convergence theorem. See, this K, as pointed out earlier, thanks to your question, can be unbounded, right? And on the diagonal. And so what we'll do is we'll make the kernel here, the integrand, I should say, integrand bounded by taking the minimum of the kernel and some constant m, and then we're going to let this capital M go to infinity. So this is just a monotone convergence theorem right here. And now I want to use that fact earlier mentioned, that if you've got a sequence of measures that are converging weak star, that the integral of your lower semi-continuous function against that limit measure is less than or equal to the limit of that function against the sequence. So that's what's expressed here. So this is lower semi-continuous. Our K is lower semi-continuous. This minimum of these two quantities is lower semi-continuous. And even with respect, now we have weak star convergence. The mu n stars go to mu, and it's easy to show that mu n star cross mu n star goes to mu cross mu. And so we have weak star convergence, and therefore I'm using that inequality to get this one here. Everybody good with that? All right. Next step. Okay, so the next step is this. I want to compute, essentially compute this integral here. So this is an integral over a discrete set of points. They're n squared points. So imagine a grid, okay? An n by n grid of points, n squared points. And think of them as points either on the diagonal or off the diagonal, okay? If it's off the diagonal, then well, I get a 1 over n squared because I get 1 over n from each one of these guys, right? Gives me this guy right here. If I'm off diagonal, I is not j, then this quantity is certainly less than or equal to just the kernel evaluated at xi star, xj star. Okay, everybody good with that? So this is certainly bigger than or equal to the minimum. So these are for the off diagonals. Along the diagonal, so here we have the two, these are diagonal entries. Okay, I don't know how big k is, but this quantity here is no bigger, right, than, it's going to be no bigger than m. So that's cool. And how many terms do I have? I have n. So what do I get here is the following. This expression divided by n squared. So I have a lim and a lim nth, 1 over n squared. This guy here is just the minimum energy, right? Because these are the minimizers, the xi stars. And here I have a quantity that is bounded bigger than m. So this is no bigger than m here. Okay. So I should have had here a minimum. Sorry. So there should be an m here, not a k. There should have been an m here. So cross this out and put an m here because we're on the diagonal. Okay. So, and so we have an n times m here. Here we have the energy, and now we're essentially done because as n goes to infinity, this ratio that has a limit which we call tau, respective transfinite diameter. Here we have an n times m over n squared, which is just the 1 over n term that goes to 0. And so now we're looking at the energy of mu is less than or equal to tau. But tau we just showed is less than or equal to the minimum energy, right? So that says a couple of things. One, that this constant tau is the same as ik of mu a, because this guy has to be equal to ik of mu a because this is a minimizer. This is the smallest, and this guy is bounded by it. So it too is an equilibrium measure. And so therefore we get that tau is equal to W, and that if you look at any limit measure, weak star limit measure, it's going to have minimum continuous energy. In other words, give us the constant W. So okay there. Everybody good with that? Okay. Any questions about proof here? So that's all there is to that argument. Okay, so let's see how we're doing time. All right, so what about uniqueness of the measure? And I'm thinking about the equilibrium measure for the continuous problem. What can we say about uniqueness? Here, what we will do is use classical techniques. We want to, we'll use kind of Hilbert inner product type arguments to prove uniqueness. More or less a kind of convexity, a standard convexity argument. So let's go through that standard convexity argument. So first of all, let me introduce our inner product, so to speak. I call it here a joint energy, a mutual energy. If you have two measures, here, these two measures, mu and nu, positive Borel measures on the set A, and we'll think of K as being non-negative to make our life easier. And we will define this double integral where we're taking an integral with respect to mu cross nu now as the quote inner product of these two measures. Energy inner product. Yep.
Previous year, that was a much sort statement of error zero. To get more quantitatively convergence to the additional
Yeah. This is a whole other areas of looking at Wasserstein type of convergence or discrepancy kinds of results that require additional hypotheses. Okay. So this is extremely general, as we pointed out, for general kernels and so on. So I'm not going into that here at this point, but yeah, that certainly, if we have more information about the specific kernel, about the set A, then we can say something about rates of convergence. Those might be in terms of discrepancy or Wasserstein type of criteria, this Wasserstein distance that sort of thing. But yeah, that's a very important area to look into. But it does require more hypotheses. Right now, we're doing very general stuff. Okay. So we're talking about uniqueness, and I want to introduce an inner product, so to speak, here, and that's just this double integral of the kernel against mu cross nu. And then I define, this makes sense perfectly for positive measures, but we can extend it to signed measures. So we definitely need to extend it to signed measures. And when we talk about signed measures, we talk about there being a positive part and a negative part, the so-called Jordan or Hahn decomposition of your measure. We can define this inner product or extend the definition in a natural way, provided we do not encounter an infinity minus infinity situation. So I can go through here and list all these things that will assure that, but I'm not going to take the time to do that here. Okay, but rest assured, it's an annoyance, but it can be taken care of. All right. So then we talk about strictly positive definite kernels. These are the kinds of kernels that are going to give us uniqueness for our continuous equilibrium problem. And that's a kernel with the following property that is strictly positive definite. If you take any signed Borel measure, nu here, so that's what that represents. So by the way, its energy, we just take the inner product of nu with itself, that's just its energy, is well defined. Okay, so if this is always well defined, it's always non-negative, and it's equal to 0 if and only if your measure is the 0 measure considered on the algebra, the sigma algebra of Borel subsets of the set. That's strict positive definition. And in practice, we often encounter something a little bit weaker than this, and that's what we call conditionally positive or strictly conditionally positive definite. That's kind of a mouthful, so I apologize for that. But we'll use this notation here to save us some breath, SCPD. So strictly conditionally positive definite. What is the difference between that and the previous definition? Is that we're not assuming this non-negativity and equality to 0 for all measures, but only those measures whose sort of total mass, its algebraic mass, is equal to 0. U with A is equal to 0. Then you will have a non-negative energy if equality will hold if and only if that measure is the 0 measure. So the theorem is, and this is just a standard type of result, that if K is a symmetric lower semi-continuous and strictly conditionally positive definite on A cross A, and it's finite Wiener constant, then the equilibrium measure is unique. So how do you do this? It's just a convexity kind of argument. So what we can do is appeal to convexity. So so the first thing that we observe is the following. Let's suppose we have two measures. The usual way of proving uniqueness is we'll suppose we have two minimizers and show that they're equal. Okay, so here those guys are called mu1 and mu2. And so we'll look at the difference, mu1 minus mu2, and look at the energy of this signed measure. And if you expand this out, you can see, just using familiar inner product manipulations, we get that the inner product of mu1 with mu2 is less than or equal to 1/2 of the total energy. In other words, the inner product of mu1 with itself plus the inner product of mu2 with itself, like this. And with this strict conditionally positive definite condition, this is going to hold, this equality here is going to hold if and only if mu1 is equal to mu2. Should have hit myself. Okay. All right. So here's the trick. As usual, we have two of these guys which are minimizers. We take the average of them, and we're going to get a contradiction unless these two are equal. So let's go ahead and plug that guy in. So let lambda, define lambda to be the average of this mu1 and mu2. And I want to compute the average of the energy, I should say, of lambda, of this measure lambda. So in other words, I'm taking the inner product of this guy with itself. And so when I expand that out, I'm going to get a fourth, right, from this 1/2 here, the energy of mu1 plus a fourth energy of mu2, and then a half of the inner product of mu1 with mu2. All right, but let's think about what these quantities are. Let's think about what they are. This is just a minimizer, so its energy is the Wiener constant. So I replace that energy by W sub k here. And this energy, again, is the minimizer, W sub k. And here we have 1/2 of this inner product, right? But 1/2 of the inner product is, thanks to condition 3 above, 1/2 is less than 1/4 of the sum of the two energies, which is sum of these Wiener constants. So if you compute this out, you simply get W sub k of A. And where did you start? You started with the energy of measure lambda, right? Which is bigger than or equal to W sub k of A, right? So this guy is bigger than or equal to W sub k of A. So you have equality throughout, which means you have equality in this inequality 3. So what is true? That equality holds, oh, this is 3, 5, it should say 3. There's equality holds in 3 here, and it implies that mu1 is equal to mu2. Okay. Equality holds here, so mu1 is equal. Okay. All right. So I'm wondering if we could, maybe this is a good time to take a break before we get into Gaussian kernels and example here. Anybody want a break? Yeah. Okay.
No.
Insisting. Okay, I want a break. So let's break for what, 10 minutes or so? All right, great. Think they heard me over there?
Okay, so let's start again. Okay.
Okay. Welcome back. I hope we haven't lost too many people here. Yeah, I want to just remind you that we were talking about uniqueness problems for equilibrium measures, and we introduced the notion of strict positive definiteness, and more generally, strictly conditionally positive definiteness. And the theorem was this, that is for such a condition on positive definiteness, we'll have a unique equilibrium measure. So a standard kind of convexity argument. Now, one of the places in some of the most important places we run into this is with a Gaussian kernel. So Gaussian kernels are strictly positive definite. And that comes from this representation. So basically it follows that from the fact that the Fourier transform, as you all I'm sure know, of a Gaussian is essentially itself. They take a Fourier transform of Gaussian. So when you look at this energy for the typical Gaussian here, you can represent it in terms of the Fourier transform of the measure mu against a positive quantity. So we get here clearly the non-negativity. Yeah, you have to kind of argue a little bit more carefully to get the equality to 0 if and only if the measure is 0. But basically that's the argument, is just to use the Fourier transform of the Gaussian, and you get strict positive definiteness. And in fact, the same argument works. Remember I told you how we could relate more general kinds of kernels to the Gaussian. And if you have kernels, any kernel of the form where it's a function of the distance between points squared, where that function is completely, strictly completely monotone, Okay, so that means that the function has a fixed sign, its derivative has the opposite sign, and so on and so forth. You keep alternating signs as you take higher and higher derivatives. And such functions can be represented. This goes back to a theorem of Bernstein and Witter, that you can represent such functions, completely monotone functions, as sort of a Laplace transform of a positive measure. Okay? And so then you can apply this kind of argument here to this expression and get the strict positive definiteness for that general class of kernels. So this will include, for example, the Riesz kernels for S positive. Okay, so that was uniqueness issues. And now, how about coming up with a way to decide whether something is an equilibrium measure? So, okay, you have a suspicion that some measure is this equilibrium measure for this continuous energy problem. How can I verify it? Give it a certificate, as some people would call it. Okay, how are we going to do that? For example, suppose I know that I have a measure, probability measure supported on my set. I know its potential is constant everywhere on the set. Well, if you've got that situation, you got to think that that's got to be a minimizer, right? An equilibrium. Because if there was not equilibrium, you'd have mass moving from one part of your set to another. Your potential would be changing, right? So if you found an equilibrium measure whose potential was everywhere constant on the set, you're going to say, hey, that's the equilibrium measure. And you can verify that, and that's an easy argument to verify. More generally, we have available what is called the Frostman criteria for equilibrium measures. And what that Frostman criteria says is this: the usual assumptions on our kernel K. And if you've got a measure mu, it is that is a K equilibrium measure. So suppose mu is an equilibrium measure, then its potential will have the following properties. Its potential anywhere on the set A is going to be bigger than or equal to the Wiener constant. Well, not everywhere actually, but quasi everywhere. Quasi everywhere means except for a set of capacity 0. Now, that can often be removed and replaced just by everywhere if we have a situation where we have a smooth kernel. Our set A is what's called regular set. Okay, and so Alex Velasquez will talk more about this in the tutorial section about when we can remove this quasi everywhere assumption and just replace it by everywhere. But basically, for things like if you're working on an equilibrium problem on a sphere or on a ball, some nice set, and you're dealing with Riesz potentials, then it's going to hold, the conditions are going to hold everywhere. So that's one property, that the potential is always bigger than or equal to the Wiener constant. And the other is that the potential is always less than or equal to the Wiener constant on the support of your equilibrium measure. So in fact, you have equality on the support quasi everywhere. Okay, potential is quasi everywhere, constant and equal to the Wiener constant of support. And moreover, these properties of characterizing the equilibrium measure. In other words, if you're clever enough to come up with a probability measure, mu, on your set A, whose potential is bigger than or equal to a constant C, quasi everywhere on A, and whose potential is less than or equal to that same constant C for all X in support of mu, then it's going to be the equilibrium measure. Okay. So how do we prove this? I'm not going to prove all of it. Let's see if I got my numbers straight. Yeah. Okay, so I got my numbers straight here. So we'll just deal with this guy right here. Let's prove this inequality. How do we prove it? So the way we're going to prove it is to argue by contradiction. We'll suppose it's not true, and then we'll produce a measure that has lower energy. So that's the argument. We're going to perturb the equilibrium measure. So here we go. Suppose to the contrary that this set where the potential is strictly less then a Wiener constant has positive capacity. So that would mean, well, since we can think of such a set as the union of sets where the potential is less than or equal to the Wiener constant minus 1 over n, that there'll have to be some n, some integer n, where the potential is less than or equal to the Wiener constant minus 1 over n. Okay. And that this set, which by the way is going to be a closed set because of the lower semi-continuity of your kernel, this is going to be a closed set. And we're going to suppose that this has positive capacity, which means we're supposing that this Wiener constant for this set Tn is finite. So remarked, okay, I've remarked that the set Tn is compact. And because it's compact, there's a problem and has a finite Wiener constant. We know that there exists an equilibrium measure, a probability measure, such that this probability measure has finite energy. You can think of the equilibrium measure on the set Tn, for example. And we also observe this: if we take this inner product of this mutual energy of tau and mu, mutual K energy, here it is written out as an integral, and use the definition of Tn being bounded above by W minus 1 over n, and the fact that this tau is a probability measure, we get an upper bound of W minus 1 over n for that inner product. Okay, so now what do? We perturb our equilibrium measure. So mu here stands for equilibrium measure for our problem, and we're supposing to the contrary that this holds, and we're going to perturb that equilibrium measure mu, and that will produce an equilibrium measure which here is denoted by mu sub delta. How do I perturb it? Well, I will take this measure of tau from above, okay, this probability from above that's supported on T sub n, and multiply it by a small positive number delta. And to make sure that I stay within the class of probability measures, I will then multiply mu by 1 minus delta. So what I'll get here then is a measure mu sub delta, and I want to look at its energy. And I claim that this perturbation for delta small enough is going to give me a smaller measure. It's going to contradict the fact that we have mu is the equilibrium measure. Okay. So what is the energy of this perturbed measure? And again, we just use the inner product kind of thinking of this guy inner product with itself. And here it is written out in that way. So we'll get a 1 minus delta squared, the energy of mu. Then we'll have a delta squared energy of tau. And then we have twice the 1 minus delta times this inner product here. All right. So we replace these numbers as follows. Replace this energy by what it's equal to, which is the Wiener constant. We replace this energy again. We leave this energy as I sub k of tau. We use the inequality for this guy here. Okay, namely the inner product. This is the inner product of tau and mu, which is the same as the inner product of mu and tau, and that is bounded above by this Wiener constant minus 1 over n. So, okay, so everybody good from this line to that line, right? Okay, there, it's nodding, yes. All right, so now we just have to stare at this a little bit. And what do we have here? We have the Wiener constant, which I'll pull out here. Then we have delta terms and we have delta squared terms, okay? So we have a delta term, we have a delta squared term. So the delta term is right here. It's minus 2 delta over n. And the minus sign is what's key, right? The minus sign is what's key. And then we have a delta squared term times this quantity right here. So this is a finite quantity. Fixed n is fixed. Finite quantity. So what matters is when delta is small, this term dominates, right? So it dominates this delta squared term. And what we end up with is for delta small enough, we get an energy which is strictly less than the Wiener constant. So if delta small enough, we contradict that the Wiener constant is the smallest possible n. Okay, everybody got that? So it's just a simple perturbation argument. So I haven't gone into the proof of the second part. So these are all available. This is available in our book on discrete energy. Okay. So now I want to try to be starting to be a little bit more specific about things I want to work on in Euclidean space. And before that, I really wasn't working in. I was working in general metric spaces, very general kernels. Okay, so now we're going to deal with sets only with their compact subsets of Euclidean space. We'll use Euclidean distance everywhere. And here is our Riesz kernel, rewritten again. So the subscript S denoting the sort of strength of the interaction. So if two particles are close to one another and S is very large, this guy's going to be very, very big, right? So the larger S is, these are repulsions. So these kernels are repelling kernels. And the larger this S parameter is, the greater is the repulsion. Now, when S is 0, this doesn't make a lot of sense. And what you do typically is take the limit, not of this expression as S goes to 0, but the derivative. So you take the derivative with respect to S, and that gives you your log of the reciprocal distance kernel. That's k sub 0. So that's referred to as the log curve, right? And we'll just eliminate the sort of k sub S subscript and just write S, whenever we mean the Riesz S kernel. So this is the regular energy, this is the minimal energy. And these are common types of kernels. So for example, if you're in 3 space and you just have your kernel is just reciprocal distance, 1 over absolute x minus y, that's the Coulomb kernel. And more generally, when S is 2 minus the dimension of your space, then you have the Newtonian, also called sometimes the Coulomb kernel or the harmonic kernel. So the crucial point being that these kernels give you the fundamental solution to Laplace's equation in RP. Okay. So those are particularly nice. So one of the connections I want to make is between these Riesz S kernels, studying these Riesz S kernels, is with the problem of best packing. So you'll be hearing a lot about that at this meeting, best packing problems. And here I'm going to be talking about best packing on a compact set, not best packing in all of RD or RP or anything like that. But just I have a compact set. What do I mean by best packing on a compact set? So given an arbitrary set of points, endpoint configuration on my set A, I'm going to look at the separation distance for that set. What is that? That's the minimum pairwise distance between points of my set. And that's going to be denoted by delta of omega n here. And the problem then of best packing is to maximize that minimum distance. So best packing is maximize the minimum pairwise distance between points. So you take the soup over of all these delta of omega n's, as omega n is allowed to vary throughout A, as Cardinal and n is emphasized here. So and omega n star here will denote for the moment just a set of points that attains that best packing property. Okay. So the connection is kind of very simple. That if you look at S, remember that's the strength of our interaction. If the strength of our interaction gets bigger and bigger, it goes to infinity. You have, maximum sort of repulsion. That gives us best packing. So more precisely, if you take the minimum S energy for n points on the set A, raise it to the power of 1 over S, then you get a limit. And that limit is simply 1 over the best packing distance on the set A for n points. And moreover, every cluster point of the set of S energy minimizing points configurations is a best packing configuration on A. So bottom line is, as S goes to infinity, if we look at these points, they're going to best packing. How do I prove this? It's easy to see this if you just take 1 over s power of a sum of numbers, you know, and let s go to infinity. Then what survives only is the largest of those numbers, which gives you the smallest in the denominator, so on. Okay, and so that's a sort of straightforward kind of exercise. Yeah.
Excuse me, do you think that there is some kind of asymptotic expansion in 1 over s or something? Is there some result where you can say that how you reach that limit? Super interesting.
Yeah, it is, and I don't think I have a picture with me in my slides, but I can show you how it increases with s. So it seems monotone, in fact, but that's not what you're after. But how? Yeah, I don't have an answer to that question, but there is some. Yeah, there's some nice numerics that we've done. Okay, to look at, but yeah.
You know, the work that Andre has to do. It's interesting to think about what you have.
Okay, when I talk about 5 points, we'll do that.
Okay, great.
You're on. That's exactly what I perfect time to do. Okay. So one of the big challenges is to determine n minimal s energy points. So how do I actually determine n points? Okay, so we can do some stuff numerically, and we'll show you that. I plan to show you that in a minute. We want to find minimum s energy points. So if we're on a circle, right, if we have n points and we're on a circle, and we want to minimize the s energy, let's say s is positive in the log case, then everybody is going to know the answer, right? So the answer is simply shown here in this picture. You just take points that are equally spaced on the circle, right? Everybody's going to guess that. But of course, you have to do more than just guess that. You have to prove it. So I think the initial proof of this, that these equally spaced points are minimizers, is probably due to Thayer's-Toff. Is that right, Doug? You think? Thayer's-Toff, they're equal points on the circle.
I think the winding.
Yes, the winding number argument that Thayer's-Toff, you know, determined the best packing in R2, that famous problem that years ago. So yeah, so the exercise here is to actually prove that this guy is the minimizer. Okay, and there it's basically a convexity argument. Okay? So essentially, it's a convexity argument to do. But so have fun with that. Okay. All right. So now, when life gets more difficult, when you go to the next dimension, so you look on S2, and there's a problem here. So where S2 is the unit sphere embedded in R3, and yeah, we can answer things kind of. We can sort of quickly come to an answer. Okay, I'm not saying we can justify it immediately, but if we have 2 points and we put it on this sphere, certainly we're going to put them what? Antipodal, right? And that's going to give us our minimizer. If we have 3 points, where are we going to put them? Yeah, on the equator, right? Put it on some equator or a great circle, equally spaced, right? A 4.
So I have a theorem. 2 points on the equator, 3 points on the equator.
Okay.
By induction.
Are you a physicist? A physicist theorem. Okay. What about 4 points? I think I show it there. The answer is shown there. All you have to do is look at it. So 4 points is what? Tetrahedron, right? So everybody's cool with that. And you all should be able to prove that. Of course, the nice thing is that the distances between these points, they're all equal, right? So you can make use of that in your argument. So you should be able to give some kind of argument, put together an argument for that. So if you guys are so smart, what's going on here? Somehow things have frozen. Oh, batteries run low. Sorry, I got to plug in. Somebody can give me a hand here? So, time out for a battery plug-in.
I see.
All right. Okay, so the exercise is to sort of prove these claims for small n. But now, what I was starting to say is if you guys are so smart, what's the answer for 5 points on the sphere? That's 2. So I want to put 5 points on the sphere. So that's to minimize the energy, right? It's just 5 points. Simple problem, right? 5-point problem. Any volunteers? You have not seen the answer already, that is. Yes.
I'll throw it out there. Not this is right, the pyramid.
Okay, what describe the pyramid?
So the square of
Okay, a pyramid with point at the North Pole and 4 points on some line of latitude, right? Okay, great. Any other suggestions?
I would put 3 like a triangle, 1 up and 1 down.
Oh, that was my guess. Yeah. Okay. So those are 2 really good guesses. All right. So let's look at them. These are 2. And they're the only 2 that come up numerically, right? If you try to just run 5 points and minimize stuff. So which one wins?
Depends on this.
Depends on S is one answer. You haven't heard this lecture before, have
No.
you? Okay, so depends on S, and he's absolutely right. It depends on S. And this is an old graph that goes back to Melnick in 1977 as a chemist who was studying configurations on the sphere. And what he plotted was the S energy of the bipyramid. So the bipyramid was your suggestion, and divided by the S energy of the optimal square base pyramid. Okay. And so whenever that ratio is less than 1, the bipyramid wins. And whenever it's bigger than 1, the square base pyramid wins. Okay. So you have to look here. Here's 1. And what you see is you get less than 1 if your Reese parameter, so the horizontal line here is the Reese strength S. If that strength S is less than a number S star is about 15, 15.04, so on and so forth. Okay, and whenever that S parameter is less than that constant, you get the bipyramid. Okay, and that's what they were conjecturing. And whenever you're bigger than this special number S star, you get the square-based pyramid. Okay. All right. Now it turns out that a few years ago, part of this, a big part of this, but not the complete truth, has been established by Richard Schwartz at Brown University. So the fun part is, it only took him 150 pages to deal with 5 points, and it's computer assisted. Okay, so it's totally just hard to believe, but okay, it was a tough argument. And what he was able to show was that indeed the bipyramid is optimal in this range, and that he could go a little bit beyond S star and show that there it's not optimal, but the square base pyramid is. So the current status of the situation, of the problem, is that it's rigorously proved for S up to about S star plus epsilon, plus a little bit. Okay, and beyond that, it's an open problem. Beyond that, it's an open problem. What happens as S gets larger and larger? And now, Doug, this is your time to chime in.
Go ahead.
But S infinity is proven, right, for up to large numbers.
Oh, S is infinity, which is the best packing problem.
Yes, which is a strong.
But the best packing problem of 5 points on the sphere has infinitely many solutions. It has infinitely many solutions. Okay.
So Ed, what is the limit as S goes to infinity? How does that?
So this is fascinating now. Okay. So remember I said, oh, as S goes to infinity, these minimum 5-point energy guys has to go to the best packing, right? But the best packing problem, you put 5 points on, that you get a square root of 2, it's the optimal distance, right? And there's lots of ways to attain that, not just 1 or 2. There's infinitely many ways to attain the maximum. The distance is the square root of 2.
Is it infinite because of symmetry or is it?
No, you can actually, no. So we're forgetting about symmetry or reflections or anything like that. No, they're different, distinct, geometrically different. Okay, not congruent. So what happens as S goes to infinity? Right? Start off with 5 minimum energy points. That's it. Let S go to infinity. Well, according to the theorem I just wrote, the sequence ought to have a limit, which is the best packing guy, right? Which one does it choose? What is the limit? So, well, I think you might guess from here, right? Where the pyramid, right? So actually, we're able to prove, Doug and myself and Andrei Bondarenko some years back, that the limit as S goes to infinity is going to be the square base pyramid with the vertex at the North Pole and 4 points on the equator. So that is indeed the limit. So it picks out that particular best packing configuration. And so there is a theorem there somewhere, a general theorem about how these discrete points and discrete minimizers will pick out a continuous minimizer when there's more than one, when it's not unique. That needs to be investigated. That needs to be looked at. That's an interesting problem. Okay. So the moral of the story is the following: is that optimal recess energy configurations in general depend on S. And that if you want to give rigorous proofs of computational observations, they can be indeed quite difficult. So, all right. Well, all we have to think about is like Kepler's conjecture, right? Kepler's conjecture about best packing problems is an extreme example of that, right? Would it take about 400 years to solve that? Which is how do you stack cannonballs in an optimal way in 3 space, right? Or oranges if you want. These days, better to stay away from these more like materials. So we want to stack oranges. How best to do that? So that answer was known years ago. It's obvious how to do it. But actually, to rigorously establish it took quite an effort, dramatic effort. Okay, so we can say in the case of the sphere, putting points on the sphere, we can say a lot more. We have a lot more tools to work with, and namely we have linear programming methods. And linear programming methods, Daniela Rachenko will be talking about linear programming methods. And so we have spherical harmonics, fantastic tool if we're working on the sphere. And I'm not going to go into detail here, but you should all have some at least nodding acquaintance with the Cohen-Kumar universal optimality theorem on the sphere. So I'm just going to state this. I'm not going to go into detail. Maybe Doug will have time to do the presentation on the sphere in terms of proving things and so on. But let me just acquaint you with this result if you haven't seen it before. And it starts off with talking about spherical design. So what do we mean by spherical design? So we're working on the sphere SD embedded in RD plus 1. And we're talking about endpoints. And we're claiming that such a set of points is going to be a spherical M design. So we have these endpoints. They're a spherical M design if it has the following property. If no matter what polynomial you take of degree at most M, the polynomial is up to degree M, you can compute its integral with respect to the uniform measure on the sphere, probability measure on the sphere, uniform probability measure on the sphere. You can compute its integral simply by taking the average of that polynomial in those endpoints. So that's called a spherical design. It's called an M design because it holds up to polynomials up to including degree M. Okay, so some typical examples of this is on your unit circle. If you look at the vertices of any inscribed regular n-gon, that's an n-1 design. You look at a regular simplex, d plus 2 point regular simplex, that's a spherical 2 design. Famous icosahedron has 12 vertices, is a 5 design, and so on. So what the idea of Kone-Kumar was that there are special designs that have really nice properties. And these are called sharp codes. So a code, sometimes use the word code, sometimes just used for a set of points on the sphere. So it's spherical, so this is a sharp code. What does that mean? It means, first of all, that it is a design. It's a design which here is denoted by 2k minus 1. It's a 2k minus 1 design, but it has some special properties regarding its inner products. Namely, if you take the inner products between distinct points of the set, you will have at most k different ones. Most k different inner products with a 2k minus 1 design. And some examples of sharp codes are these, the vertices of the regular n-gon, the points, the vertices of the regular d plus 1 simplex. Here we haven't mentioned yet the E8 lattice, but the set of roots of the E8 lattice on S7, there are 240 of them. They form a sharp code. And similarly for Leech lattice, they are normalized to lie on S23. The shortest of those vectors is non-zero vectors in that lattice, of which there are 196, 560, as you all well know, form a sharp code. And so the wonderful theorem of Kone-Kumar concerns universal optimality. And by universal optimality, what we mean is that a point configuration, endpoint configuration, is universally optimal if the minimum k energy of endpoints on SD is given by that endpoint configuration for every kernel of this format. Namely, take any kernel, and we're talking about a fixed number of points, that it works, it's optimal for all these kernels that can be written as an absolutely monotone function of the inner product between x and y. And that, if you think about points on the sphere, the square distance between points on the sphere is simply given by this expression, 2 minus twice the inner product or dot product of x and y. So you can also write this in terms of equality, giving you minimum energy for all, say, functions, completely monotone functions of distance squared. Okay, so you can also rewrite this in terms of kernels that are functions that are of square distances, where the function is completely monotone. Okay, so so the famous theorem is this: if you take any sharp code on SD, then that is universally optimal. So if you can find a sharp code, that's not a simple matter at all, finding sharp codes, then it will be universally optimal. So it will work for this large class of kernels to give you the minimum energy, the minimal possible energy. So if you're looking at S2, for example, there's only a handful of configurations that are sharp, codes. And that occurs for 2 points, 3 points, 4, 6, and 12. That's it. Finite, just a finite number. So just small n. So this is typically a small n type of result, which gives you optimality. Okay, so that's basically all I want to say. But I want to go on to what we've been focusing on research-wise for the last number of years, and that's sort of asymptotics. What can we say about asymptotics as we let n get large? But looking at fixed n problems, low n, they're challenging problems and important problems. But okay, but we've gone on to look at asymptotics as well, and we want to know, what do these minimum energy points look like for large n? So the first thing that's fun to do is just run an experiment. Take your sphere, S2, the unit sphere, and R3, and try computing the minimum S energy. So take S, I think I took here, S is log, the log case, S is 0, and also Coulomb case, 1 over distance between points. And I had a graduate student who was extremely talented. That's very important criteria in order to solve any difficult research problem, is to find somebody who is talented graduate student who can prove theorems and also run, do programming and know some computer software. So I was fortunate in having one such student by the name of Saff. And he ran a bunch of experiments for n up to 2, from 2 on up to 200. So 200. I'll show you why he stopped at 200 in a minute. So this is a number of years ago, and there are a lot better computations now. So I'm sort of giving you a little bit of my personal history here. Okay. And so it turns out, like any experiment, that there's typically bad news, and there's also some good news. So let me show you the bad news. So here's the bad news. So the bad news is shown in this picture here. So what you have is the bottom line is the number capital N. That's the number of points that you have. And every point, every dot on that bottom line represents a global minimum of energy. If there is a dot above it, then there is a relative min that is not global. All right. So look what's happening here. N is, wow, small, it's essentially unique. So when I talk about minimizers, and somebody asked here, we're not considering reflections, rotations, right? That's all. So we all normalize things so that all of them are taken care of. But I'm talking about geometrically different configurations here. And as what you notice is that as n gets larger, well, you get more and more of these dots here above here. And that spells trouble. In other words, you're looking for the deepest valley, you get stuck in some valleys that are not quite so deep. And there are more and more of those shallow valleys as n gets larger. So what's the conjecture here as to how many relative mins there are relative to n? What would you guess? It's the standard conjecture. This goes back to Erber and Hockney, is that, yeah, that it should grow exponentially. Nobody has a proof of that. And I'm not sure that that's true for all n. It may just be for a subsequence that it's true. There are some nice n's, so to speak. There are not, some n's that are nicer than others. But the conjecture is that the number of relative mins grows exponentially with n. But that shows you the nightmare of the problem of doing computations. So if I show you an answer, yeah, well, you've got to take my word for it somewhat, okay? Because I can't. Once n gets large, it's going to be almost impossible. Because any trial,
And the baseline is all empirical, right? And there's no proof for this.
Exactly right. That's right. It's running running the program 1,000 times and so on. Okay,
Because for the packings, you have exact solution.
yeah. For packings, you have exact solution?
Well,
No,
I
you
mean,
don't.
maybe not for 100, but I mean,
Yeah.
the strong packing problem solved by mapping this to planar graphs.
Okay.
You enumerate planar graphs and then you
Yeah, like all of
Okay.
these.
Contact graphs. All right, but there is a little bit of good news in this picture. So look at this vertical line here. And remember what we're plotting is the difference between local and global, right? So if you look over here, you see that the scale here is in hundreds, 0.01, 0.02, and so on and so forth. Now, if you think of like 100 points, N is, capital N is 100. What do we know? We know that the energy grows like N squared, right? So the energy the minimal energy should be roughly on the order of 10,000, right? 10,000 for 100 points. Okay? But the difference between the relative mins and the global min are in the order of hundreds. Hundreds. So if you land on some local min that's not a global min, you're still pretty darn good. You're really close. That's what we see here, but there's no general theorem. This is a beautiful open problem. What happens? What can you say about the energy from these relative min? All our numerics seem to indicate that you are very close. If you can find any relative min, that on a relative scale, you're doing very well in terms of the energy. All right. So, we should go back here and say, there is good news. Besides what I just told you, there's good news, which is that the equilibrium points try to distribute themselves over a very nearly spherical hexagonal net. So remember, we're talking about S2. So hexagons are sort of what we expect. And my graduate student was rather artistic. Okay, so enjoy and created this picture, which is a great picture because it shows what? It shows the plane R2, and it shows best packing problem and best covering problem still in R2, which is the equitriangular lattice or hexagonal lattice here. Okay, now, okay. So let me talk about this picture a little bit first. So here, these are 122 electrons. So electrons means I'm taking S equals 1. Okay, so they're just I'm thinking of them as electrons on the sphere. They're repelling each other according to inverse distance between points restricted to the sphere. And so here's the 122 points, these yellow dots. And from that, we created a soccer ball, okay? Or football in your sense, right? So with Voronoi cells. So for these polygonal regions here, these are Voronoi cells or nearest neighbor cells. So a point is in here if it's closest to this dot than to any of the other dots, right? Okay. So that's a Voronoi cell. And with that, we get a tessellation. Okay. So here's what the tessellation looks like. And it kind of looks like a soccer ball, right? Soccer ball, y'all remember your soccer ball statistics? So soccer ball has patches on it and hexagons on it and what else? Pentagons, right? So the hexagons, how many of them are there? God, you've been growing up playing soccer, so you guys know.
No, we do not.
Oh, so there are 20 hexagons and 12 pentagons, right? So on that, okay. By the way, the soccer ball, you all know, is sort of an amazing object. I'm talking about the classical soccer ball design. Now they paint over them with other kinds of funny designs, but the 20 hexagons and the 12 pentagons, that's the same as the form of carbon-60, right? So in 1996, Proto, Small, and Curley won Nobel Prize for discovering carbon-60, C60. What was C60? C60 was that ball you've been kicking around when you were a kid, okay? That's what C60 is. That's exactly the structure of carbon-60. Okay, So what we have here. Oh, by the way, so obviously this ball is showing a lot of hexagons that are kind of regular, like I want to be hexagons. That's what it's saying, right? But, oh, and this is an important question for France, by the way. So we have someone here from France. And because, what's another name for France? The hexagon, right? Another name for France is hexagon, okay? All right, and it's thought of and taught in the schools, right, as the borders of, or the coastlines of France, they form 6 portions, and so it's regarded as a hexagon. And so the question that I posed was, can you cover the Earth with copies of France? Right now, for the French, that's an important question, right? So, and so if I try to take this flat piece of paper, and cover it on, put this on this curved surface, it's not going to happen. Then I'll be able to do it and keep all my hexagons, right? I'm going to have to cut the paper or, piece it together, right? There's going to have to be something that allows me to count for this curved surface, which is what's happening here, right? So you have pentagons here, and okay. All right, so let's look at more points. Here's 160, I'm sorry, 1,600 points. And these are minimum energy points, and you have to take my word for it, that this was done. The reason why you should have some confidence in this picture is because I did not compute it. All right, it was done by Rob Wormersley. He's at UNSW in Australia, who's got quite impressive. Right? Also, some computations that were done by Doug and Alex Valasia. So what we see here, again, showing here the Voronoi cells, and what we have is an ocean of hexagons here, an ocean here of hexagons, but we also have these so-called grain boundaries or dislocations. Depends on who you're talking to as a physicist. I don't know what you would refer to them as, but so they sort of pair up with the heptagons. So we have 7-sided figures, 7-sided Voronoi cells, 6-sided, of course, they're hexagons, and the blue are the 5-sided shapes. Okay, and it seems to be true. After doing lots and lots of numerical experiments, and this is a conjecture, is that for n large enough, the only Voronoi cells that you're going to see are 5, 6, or 7-sided. Okay, and so we're trying to understand these guys right here. We call them scars. We're trying to understand how they behave and what effect they have on asymptotics. Okay, so that's a big issue. It's a hard problem. And let me see if this is going to work. So I can't guarantee it, but this is 30,000 points that Doug prepared. Here we go. So we started with 30,000 random points. We're doing a gradient descent method. We're minimizing energy at every stage, and here's what we get. So you see again these Voronoi cells, the green, the vast ocean of hexagon, but you have these heptagon strings, so to speak, that are created here. And we'd like to know asymptotically how they behave, all right? How they behave and so on. So, Doug, do you want to make any comment about?
I think it was Alex last year.
Okay, all right. So
Although I was working.
okay. So yeah. So this animation. So we're not claiming that this is the minimizer. There are, in fact, better results than what is shown here, but they do seem to kind of form, lines of boundaries. Occasionally, you might see a button or something like that. But yeah.
But you must have a theorem saying that, I mean, you don't know what the solution is, right? I mean, for that. But you must have a theorem that in the limit n going to infinity for sufficiently large s, the optimal solution has the same value than in the planar. It becomes asymptotically planar.
No, I think that's what we're all after that. That's a hard problem.
The first order, that is our theorem. The first order, and that's what.
I can show that to you. I mean,
Yes.
It's the dominant order,
But-
we can talk about that.
I think I can show it.
Yeah, I mean, when we have S large, which is called the Poppies and Bagel theorem, okay, when S is large, we know what, you can show that there's a limit, and it behaves like best packing. But, okay.
But no, I mean,
But-
even excuse me, I don't want to take
Yeah,
that. I mean,
but-
but I mean, the football is an assembly of flat surfaces. Right? You are approximating the surface of the sphere by something flat.
Right.
Now, I think you can. I can prove that. You can do that in the limit of infinity, a going to infinity. That the non-flat parts are measured zero.
Yeah, okay. So we'll talk about, Doug will talk about this theorem where we'll talk about rectifiable sets. So not only just sphere, but sets that are almost, made up of kind of planar pieces and so on. Okay, and he'll talk about it. He'll talk about that. So that's one of our main results, so to speak. Okay. So this was just a warm up for him. Okay. So I'm going to sneak in a word or two about Snell's problem. So how did I get started working on these points on the sphere? It was due to Steve Snell, and he was in Florida. I was teaching in Florida at the time, and he was down there at a conference, and he said, "Okay, I want, can you join me for lunch? I have a nice problem for you in potential theory." So I said, "Sure," and he told me his problem. This is the 1990s, and this is a problem which is still not solved. Okay, and the problem is this. It's Steve Smale came up with 18 problems for this century. Okay, like Hilbert's list of famous problems. Smale has 18 famous problems. Okay, and number 7 is this. This is number 7. Problem number 7 is Smale. It's to produce rapidly polynomial time to produce endpoints on S2 in such a way that the energy for those points differs from the minimum energy, which is here, E0. This is the minimum S energy for endpoints, by at most a logarithmic term, by most a constant times log. So this is still not resolved. So there are various deterministic approaches. There have been some probabilistic approaches, generating points, see whether their energy is low. So remember, this guy here is growing like n squared. Remember, that's our fundamental theorem. So it's growing like n squared. And down here, we're going to talk about what might be a more precise asymptotic for it. But this guy's growing like n squared, but we want to generate points that are no worse than log n, different from this minimum energy. Okay. All right. So this going back in history, in terms of an asymptotic. So you might say, well, okay, well, what is the more precise asymptotic for the minimum energy? And it goes back to Wagner, 89, who got this estimate here. So the first couple of terms, n squared and log n, and there's a bound constant times n term. Then myself and Zhenya Rachmaninoff and Yaman Zhao, my student, 1994, a long time ago, proved the following, that if you define a constant Cn by its being a coefficient, so to speak, of n in this expansion, so this is a definition of Cn, the minimum energy equals this, then this constant Cn lies between these two quantities. Okay? So that was a long time ago that we established this inequalities. And since then, There have been a number of improvements. There's one by Dubicus. I don't remember exactly what that was, but very recently, their estimates to improve the lower bound. So the lower bound here that we got was this, but it's much improved here by Steinerberger and most recently by Lorenzen, which is a really spectacularly good lower bound. But we made a conjecture back in 2011 that this Cn here, the coefficient of n, in the asymptotic expansion of the minimum law of energy, that this guy should be, so this limit should exist and be given by this constant here, which involves the derivative of the Epstein zeta function for the hexagonal lattice. Okay? And this numerically is minus 0.05556. And you can see here Lorenz's estimate is darn good, okay, for that. So we claim that that's good, but what has been proved is the theorem of Betterman and Sandier, who in 2018 showed that, first of all, that this limit does indeed exist. This was just a conjecture, that it does indeed exist. And moreover, is less than or equal to this constant here. The limit exists and is less than or equal to this. And moreover, they showed that if you can establish the equality, you can establish that this limit equals this constant here, then that's the same as showing that the equitriangular lattice, the hexagonal lattice, is optimal for this renormalized energy in R2. It's studied by, so the argument here is based on the work of Sandier and Serfati, where they studied normalized energy, normalized logarithmic energy in R2. And so here you've got something which is sort of equivalent to what is the biggest open problem now out there, which is show that the hexagonal lattice or equitriangular lattice is universally optimal. Okay? Everybody believes it. We know the answer in 1 dimension. We know the answer in 8 dimensions. We know the answer in 24 dimensions, strangely enough, but we don't know the answer in 2 dimensions. And so that's the big challenge. It's kind of embarrassing that we can't prove a universal optimality of the equitriangular lattice. But that would make these, that would give the equality here if this conjecture is true. And so, okay. Well, I think I'm past time now, so we'll stop here. Okay, we'll stop here and continue later this afternoon. Thank you for listening. When do we regroup?
Well, it's now nice for some time.
Okay.
And Doug is going to talk
Yes, I'm still willing.
Okay. Well, I just connect here.